This is 7th lecture, and during previous lecture we were talking about neural networks, about theory behind them, and if you've done homework, you could toy with some simple examples like ANDs or operators. You could teach your neural network for doing these logical operators, and this can be considered just a toy examples. And if we are teaching neural networks on real data that's usually numerous and it's quite vast and it has a lot of features, in that case you need to know different techniques and different tips for learning real neural networks for real applications. So today this will be a little bit like practical lesson about training of neural networks. So just training of a neural network. So you can remember from previous lecture that we are defining neural network. I'll just denote it as a black box. Then we have some inputs, we have some outputs, and that's how we define it. And neural network has 3 layers, which are called input layer, hidden layer, and output layer. And after we define neural network, after we define weights, connections which totally define its behavior, we can finally train neural network. And training means that we have some X data and Y data, and then we test neural network. For example, we can show some parts of X data, then neural network computes new Y data. So then neural network computes some Y data, and we can compare it with a real one. And based on how neural network works, we can assign some test score, which we'll call loss function. And we try to minimize loss function or raise test score. So the better neural network works on this data, the less and less is loss function, and the more is some test score, or sometimes we can call it accuracy. For example, if we are classifying some things. For example, we can just have some features and then want our neural network to classify if this is an apple or a banana, and then this test score can be called accuracy. So that's how a neural network works without deep understanding of backpropagation, of just propagation. And so in the previous lecture we've completely written class which is called neural net, and it's quite easy to implement it as some Python module. So you can download this Python module called neural net lib in directory called modules, and now we can use this module like that. So we have neural net lib. Neural net lib is in the same directory as Jupyter Notebook we are currently using, and we just import this module as net. And also we are going to import some other modules which we are going to use during this lecture, like random module, pickle module. Some modules we will talk about it later, and just some other like NumPy and matplotlib, which are going to clear our code and make it more readable, and also visualize something. So when we are talking about neural network, the most important things that we need to have is X and Y labels, which we want to recreate by this neural network, which means that first we need to find data. So we are going to use data called MNIST, M-N-I-S-T, and this data includes 55,000 images of numbers. So we have an image, and its resolution is 28 by 28. So in total we have 7,084 inputs, and then we have some pixels are black, some pixels are white, and white pixels are corresponding to 0 input, and black inputs are corresponding to 1 input. And this is image, and now we can just write down pixels going like that. And using this technique, we are just converting whole image into just a list of values. And this list will have 784 inputs. And after that, we will have some neural network, some hidden layer. And as a result, we need to get 10 numbers. And because we have 10 numbers from 0 to 9, we are going to have 10 numbers which are representing a possibility of this particular number being, of this particular image being a number which this output represents. So for example, it can be like 0.9, this is 0, 0.05, 5% this is 1, and so on. You can have these values, and that's how all this data, called MNIST, will be grouped. So if we're talking about real data, our labels are going to be just lists of values with this length. And if we are talking about Y values, we are going to have a list from 10 numbers. And because we have data, we want to represent these numbers using this technique, and this technique called one-hot vectors. So when we are doing some classification problem, because right now we are trying to classify this image. We see an image and we are certain that this is 2. And so we want to tell neural network that this image represents 2. And that can be done using a list of values, of 10 values. And for example, we want to represent 2. We can encode this for neural network like that. And so we are telling neural network that probability of this particular image to be 2 is 100%, and all other numbers are 0%. So this is definitely not 3. This is definitely 2. This is what this list of values says. And that's method when we are representing classified data using zeros and ones, and we have only one, and all other values are zeros. It's called one-hot vector. And for example, if we are having like we are trying to classify cats and dog, and for example something else, we can represent a cat. We have some image, and desired y label will be 1, 0, 0. So this is definitely a cat, and not a dog, and not something else. So that's how you can represent. So representing X data is quite obvious, because we are just taking an image and just stretching it into one line. But representing Y data can be used with one-hot vectors. As a result, our neural network must have 784 inputs and 10 outputs. We remember that neural network has also hidden layer. And this number is not defined. We have to define it by ourselves. So I found one quite simple formula which can help you find this number of hidden layers. So if there is a lot of neurons in hidden layer, in that case we have a lot of weights and we can update them, and that means that neural network has like a lot of brain capabilities and a lot of flexibility, which means that it can learn more complex things. And if we have a smaller number of hidden neurons, in that case there is smaller number of weights, and neural network can learn only the simplest things. So we need to find, because of that, we cannot have too little of hidden neurons. Because if we take like one hidden neuron, then all this data and all this complexity is gone, and we cannot classify our image, and just neural network will struggle to do this, because it just won't have a weight to update, and it just won't have enough brain power to process these images. So hidden layer number of neurons in hidden layer can't be too small. Because of obvious reasons, because if we have too small hidden neurons, then in that case neural network just cannot work. But what will happen if we have too large number of hidden neurons? This can sound reasonable. We can learn a lot of complex things and a lot of variety, but if we are taking some data and this data is quite small and we have quite large number of hidden neurons, that in that case neural network can memorize all inputs and all data by itself, and then it won't work well for the other data. So imagine we have some points, x and y data, and we have some, and they are quite linear. So if we have line which represents a simple behavior and a little of hidden layer, then we can draw just this line and it will lay down quite well. And that means that if we have this linear relationship, if we find a new data point, for example, what's y value, what y value we are expecting if we have this x value. We can just draw up and say this is expected y value. And this will work just fine. But if we have two small data points, we have right now like 4 data points, and we are increasing and increasing number of hidden layers, then our neural network can do something like that. It can find special function which fits perfectly for this and only this data. But now, if we want to find some new what y value we are going to expect if we are taking this x input, we are going to get not reasonable result. Just because neural network totally memorized all features and just all points in this data. That means that if we have a lot of weights, and for example, like a number of weights is bigger than points in data, then this is not good, because neural network can just represent, can just memorize everything, and it's not going to work for other data. And we want our neural network to be as general as possible and work for as broad data as possible. So too large is not good too, and this phenomena is called overfitting. When we design neural network so excellent in this particular data that it becomes very bad in some other data, for some other data. And to prevent this overfitting, we are usually using such technique. First of all, we can take a lot of hidden layers, and we can easily check if our neural network is overfit or not by splitting all data into train part and test part. So imagine you have some x and y data. This is your whole data, and you can take like a 30%, and this will be called test data, and 70% is going to be called train data. So you are training neural network on 70% of your data, and you are splitting all this data randomly, so you without any bias. And after training, so you first train on this 70% data. After training, you can check how well your neural network behaves on test data. And if we are going to have just right number of hidden neurons, then our neural network will behave basically the same as for the trained data. But if we have a lot of hidden layers and a lot of hidden neurons, then neural network will obviously fail this test on test data because of overfitting. So that's how we are going to check, and this check is going to be a part of your homework. So let's return to a code and see. So this data, this is MNIST data. If you have downloaded TensorFlow, you can easily download this MNIST data. So you can see this is 7. That's how we can represent 7. This is 0, 1, 2, 3, 4, and 7. So this particular image is 100% is 7, and it's not our numbers. And we can even draw these numbers using matplotlib. So this is 8. And we know that this is 8, but now we need to our neural network train to tell us if this is 8 or not. So that's how we choose hyperparameters, and in our case hyperparameters are just number of input neurons, hidden neurons and output neurons. Number of input and output neurons is already defined, and for hidden neurons we can have this simple formula. So we just divide number of points in data, which is equal to 55,000, because we have 55 x and y data, images, and this one hot vectors. And we divide by number of inputs plus output neurons, and also by some factor alpha, and this alpha has to be in the range between 2 and 10. And 2 is very close to overfitting, and 10 it's close to not grasping all data and all features. So your alpha should be like 4, 5. This is the optimal one. And also sometimes alpha can depend on your data, so you still have to find this manually, and so you can check this all using test and train data technique. So we've calculated using this simple formula and get that number between 32 and 16 hidden neurons is just right. So I took 32. You can take 31, 34 as you want, as long as it keeps in this range of alpha between 2 and 10. And finally, we actually training. And for this part, we have one final hyperparameter, which is called learning rate, and it's denoted as eta. And you can remember that we are using gradient descent, which means that we are calculating gradients, and then we are moving in direction of the steepest descent. So, and this learning rate, again, we have something like that. If we have learning rate that it's too small, then computer is going to calculate all this, is going to train neural network too slow. And if we have learning rate too high, then whole training can be unstable or exponential. So, and if we have learning rate just right, then we can continue training neural network. And learning rate is usually the most hard to define, because we actually want to train neural network and then check if this is good, and then again we can adjust learning rate. So usually the learning rate is has to be found manually, just by experiment. Finding all these hyperparameters is actually can be considered as optimization problem, and this is right now quite hot topic in real machine learning. So actually all this stuff can be solved by, again, some new neural networks, which are saying you how many hidden layers or how many hidden layer neurons or how big learning rate has to be. So this can be solved by other neural networks, but we won't go in such depths. We're just going to train neural network using learning rate, which is equal to 0 and 1. You can find better results, for example, because I think that this learning rate is too low, and 0.5 can be okay too, so you can try and see where it goes. But nonetheless, we are training neural network using classes that we defined in previous lecture, and after an hour of training, so that's something that we get. you can see that I also printed out each 100 operations I am printing out calculated value, desired y value, and loss function. And finally, let's check how this works. So you can plot your loss plot, and you can check using this code how well our neural network is trained. So if you actually run this on Jupyter Notebook, and you can click, and it will just show you some random image and show you prediction of a neural network. So this is indeed a number 6. So neural network behaved quite well, and I'm not going to run this, but you can do this at home and just click and see that accuracy of this neural network is actually quite high, and so it's quite good at classifying image of a number, and that's how it goes. So now we are going to look more in depth how we can improve gradient descent. So first of all, and the most simplest algorithm you can have is just called stochastic gradient descent. And what are we going to do? So usually, as we defined in a class called neural network, we are having one x and y desired labels, and then we print some gradients, we calculate them, and then we update weights. And sometimes it's good, but usually what a stochastic gradient descent does is takes several labels, then calculates some gradient, and only then updates weights. It works better because sometimes if you are taking just one input and one output, your weights can wander quite chaotically, and if you are taking more than one input and output, and this whole structure is called a batch, and number of labels is called batch size. If we are taking quite considerable amount of this data, for example 64, 16, then our sum gradient is better than just a one gradient, and in that case weight can travel quite, and loss function will be decreasing smoothly. But if we are running with one input and one output, then loss function can look like that. So this smoothness is why we are preferring to use stochastic gradient descent, using sample size of from 16 to 500, like so. And after we've talked about stochastic gradient descent, we can finally talk about how to save all these weights, because if I am now to close Jupyter Notebook, all these weights that I pre-trained, and sometimes training can last for several hours or for several days, we need to store all these weights somewhere. And for that reason, we are using special module which is called Pickle. And what it does, it converts practically any Python object into a binary code. So you just define, for example, a dictionary to contain all weights. You define that this dictionary, it's quite simple, and then you just pickle.dump, and all this dictionary is converted into a binary code. And this binary code is then conserved into a file with .p extension, and then you can load using pickle.load and open your model. And after that, you can, for example, after you've closed Jupyter Notebook, you can return to the start, just import all libraries, then you can create, for example, a new neural network, and then you load all these weights like that. And now your neural network has the same properties and the same weights as neural network before. So you just passed all these weights into another neural network, but its behavior will be the same. And also now we are going to talk about, now we are going to probably get a break, and after that we are going to talk about libraries in machine learning. So that's it. Let's have a break.